Welcome to the ninth video of System Programming and Compiler Construction. We will continue with the fifth module of SPCC, that is Compilers Analysis Phase. In this video, we will be looking on how a symbol table is managed, how errors will be handled by compilers, what is the role of lexical analyzer, what is the difference between tokens, patterns, and lexemes, and why input buffering or buffers are required by lexical analyzer. Let us see. So in the previous video, we have seen that it is the lexical analyzer which is responsible for creating symbol table, and the remaining phases will be using this symbol table either to read data from it or to update the value in the symbol table. So what is the role of symbol table when it comes to compiler? An essential function of compiler is to record the variable names used in the source program and collect information about various attributes of each name. So basically, whatever user-defined names are used in the source program, all these user-defined names are collected into a table, that is my symbol table. Apart from noting down the variable names, the compiler is also responsible for making a note of the attributes associated with each name. These attributes can be the type of the variable. It can be, so basically when we say attributes, it is more information about the variable names which are stored in the symbol table. So what is that more information? The attributes can be the type of the variable. The function name is also considered to be a user-defined variable. Hence, what is the type of function? What are the parameters used in the function? All these extra information is to be collected into the symbol table. As I said, the attributes provide information about the storage allocated, its type and its scope. That is, what kind of storage is provided to the variable, what is the data type of the variable, and what is the scope of the variable that is used in the program. Scope means whether it is a local variable, whether it is a global variable, and so on. It is also responsible for storing the names of the functions which are created by the user. And when we say function name, the attribute information will include the number and the type of arguments. That is, when I say function, every function has some arguments passed to it. So what are the number of arguments? What are the type of arguments that is stored in the symbol table? What is the way the arguments are passed? Whether the argument is passed using call by value or it is passed using call by reference. And what is the value returned by the function? Is the function returning an integer value or the function is not returning any value? All this extra information is saved in symbol table. Thus, symbol table is a data structure containing a record for each variable name, and it will have fields for the attributes of the name. This data structure of, that is the symbol table, should be designed in such a way which will help the compiler to find the record very easily and very quickly, because the compiler will be functioning properly if the symbol table is properly managed. Hence, the selection of the data structure for creating a symbol table should be in such a way that the symbol table can be created easily. It can be, the data from the symbol table can be retrieved quickly. That is, the addition, deletion and the updation operations from the symbol table should be done quickly. Error handling routine. So we all know that during the compilation process, if any of the phase encounters an error, then the compilation process will be halted and the user is notified with the errors that are encountered. Thus, identifying errors and reporting those errors to the programmer is one of the important functions of the compiler. The error message which are being displayed to the programmer should be given in a crisp format so that it becomes easier for the programmer where exactly the errors have occurred and what is the error. As I said, errors may occur in all or any phase of the compiler. Whenever a phase of the compiler discovers an error, it must report the error to error handler, which issues an appropriate diagnostic message. That is, it is the error handler which is responsible for generating and displaying message to the user. Let us see which phase is responsible for identifying which type of error. Or in other words, whenever a specific type of error is encountered, it is which phase will be encountering that error. So, if I have any spelling mistakes done into my program, then the lexical analyzer is responsible for identifying that error, and the execution or the compilation process will stop there itself. If my program has less number of brackets or if the parentheses are missing, then the syntax analyzer will be throwing a specific error. Intermediate code generator is responsible for throwing error if the operator and the operands are not matching. Code optimizer is responsible for generating error if any statement is unreachable. The error generated by code generator is very rarely happening, but this is given, or an error will be generated by code generator if the memory is full or if the registers are not allocated properly. Symbol table is also responsible for generating error if we are using multiple identifiers in our program. The most frequent mistakes are incorrect token sequences in type, invalid character sequences in scanning, scope errors, parsing errors in semantic analysis. So maximum errors are encountered either in the lexical analysis phase, syntax analysis phase, semantic analysis, or code optimization. The remaining steps will not be encountering errors much. Let us understand the lexical analysis phase in detail. What is the role of a lexical analyzer? As I said, the main task of lexical analyzer is to read the source program character by character and grouping these characters into lexemes. These lexemes are then converted into tokens. When lexical analyzer discovers a lexeme constituting an identifier, it inserts that into the symbol table. So, whenever the identified lexeme falls into the category of an identifier, then that lexeme is stored in the symbol table. This is how lexical analyzer and syntax analyzer communicates with each other. The lexical analyzer is responsible for generating source program. The lexical analyzer is responsible for reading the source program and generating tokens out of those programs. It is only when the syntax analyzer asks for a token, the lexical analyzer will send the token to syntax analyzer. Both these phases are responsible for communicating with the symbol table, and the output of syntax analyzer is then submitted to semantic analyzer. Apart from identifying lexeme, the lexical analyzer is responsible for performing the following task. It is responsible for removing comments and white spaces. It also correlates error messages with the source program. This is very important slide. You can expect a 5-mark question or a 10-mark question on what are patterns, lexemes and tokens and how these are different from each other. So you can get a differentiating point question for 5 marks or you can get a simple theory question on this topic. Let us understand what are lexemes, patterns and tokens. So just before the slide, we saw that lexemes are identified by the lexical analyzer. So how that is done? So basically, the lexical analyzer is responsible for reading the source program character by character. It starts grouping the character based on some predefined knowledge. This predefined knowledge is given to the lexical analyzer by providing a regular expression. In other words, whenever any lexical analyzer is designed, this lexical analyzer will be provided with regular expressions. Using these regular expressions, the lexical analyzer can distinguish the identified characters into appropriate lexeme. I repeat, whenever any lexical analyzer is designed, these lexical analyzers are provided with regular expression. And based on these regular expressions, the lexical analyzer can group the characters into meaningful sequences, and these meaningful group of characters is then termed as lexeme. Once the lexemes are identified, these lexemes are then converted into token by lexical analyzer. Each token has a format of token name, token value. So I have spoken about lexemes, I spoke about tokens. Now what is patterns? So patterns is nothing but, or you can say patterns are written using the regular expression. So when I said lexical analyzer is given a knowledge of how to identify lexemes, and this knowledge is given on the basis of regular expression. So if I want to identify any pattern, or if I want to write any pattern for identification of lexeme, then those patterns are written using regular expression. Let us see what the slide says. Token is a pair consisting of token name and attribute value. Token is basically a sequence of characters that are treated as a unit, and it cannot be further broken down. As I said, patterns define the rules that the lexical analyzer uses to identify lexemes and classify them into token. These are often expressed using regular expression. In other words, we provide lexical analyzers with patterns. Using these patterns, lexical analyzer can differentiate lexeme into its appropriate type. And to write these patterns, we use regular expression. A regular expression defines a set of strings that matches a specific pattern, allowing the lexical analyzer to recognize valid tokens from the source code. Maybe in my next video, you will understand what am I trying to say with patterns and regular expressions. So in the upcoming video, I will give you an example of how to write a pattern with the help of regular expression. Last is lexeme. So lexeme is a sequence of characters that forms a meaningful unit in a programming language. It's the raw string of characters before it's categorized. For example, if I have an input which is of the form int count is equal to 10, then the lexical analyzer, based on the pattern given, will be differentiating each into three lexemes. That is, int is my first lexeme, which falls under the category of keyword. Count is my second lexeme, which falls into the category of identifier. Equal to is my third lexeme, which falls into the category of operator. And 10 is my fourth lexeme, which falls into the category of literal. So this was all about tokens, patterns, and lexemes. Let's further continue to know in detail about lexical analysis. Lexical analysis, that is scanner, is the only part of the compiler which reads a complete program. So by now everybody must have understood that every phase of the compilation process is dependent on the previous phase. In other words, syntax analyzer is dependent on lexical analyzer for its input. Semantic analyzer is dependent on syntax analyzer for its input. So every phase is dependent on the previous phase for its input. But lexical analyzer or scanner is the only phase which is responsible for reading the source program. Because it is reading the source program character by character, a considerable amount of time is wasted in reading the program. Hence, the compilation time goes low, but which is not accepted. We cannot want our compilation process to go slow. Thus, the speed of lexical analysis is a major concern. That is, we need to make sure that the lexical analysis phase is completed as soon as possible. Thus, we need to speed up the most simple but important task of reading the source program. This task is further made difficult by the fact that we often have to look one or more characters beyond the next lexeme before we can be sure we have the right lexeme. What do we mean by this? Say for example, I have this say keyword int and a. Okay. Now, if you observe, int is a valid lexeme and it falls under the category of keyword. But to group or to categorize int into the category of keyword, I will have to look one more character ahead before deciding whether int is a lexeme. If this character A was not existing, then I will obviously group int into I will obviously group int into the category of keyword. But since A is written, I have to group this particular lexeme into identifier. Thus, to decide whether the group of characters which are already read falls under which category of lexeme, we need to look one character ahead. Hence, a two buffer system is used to safely manage huge look ahead. So there is always a look ahead task associated before we categorize a group of character into specific lexeme. Let us understand this two buffer scheme. Input buffering. Before understanding what input buffering is, let us understand what is a buffer. A buffer contains data that is stored for a short amount of time, typically in computer's memory, that is RAM. So buffer is something which is responsible for storing some data for short amount of time, and the buffer are stored in RAM. It is said that accessing data from RAM is much quicker than accessing data from a disk. The purpose of buffer is to hold the data right before it is used. That is, before we start categorizing characters into lexeme, these characters will be first stored into buffer. Let us see how this buffering works for lexical analysis. Input buffering is the process of storing all of the source code in memory before beginning to compile it. That is, before the lexical analysis starts its compilation process, the source code is brought into a temporary storage, that is buffer. By having all the data readily available, compilers can read and execute instructions more quickly, resulting in overall improved performance and faster build times. There are two methods to implement this buffer. You can have one buffer scheme or two buffer scheme. Obviously, there were some disadvantages associated with one buffer scheme. Hence, the second scheme, that is two buffer, was introduced. What is one buffer scheme? In this scheme, only one buffer is used to store the input string. The size of buffer is usually equal to n characters, where n is the number of characters on one disk block. How these buffers are working, or what is the working of one buffer system? Consider that this is my source program. Before the compilation process starts, the characters are stored in buffer. Now, to read these characters, the Lexical analyzer uses two pointers. One is the F pointer and another is the B pointer. F pointer is known as forward pointer and B pointer is known as Lexeme begin pointer. Initially, both the pointers as shown will be pointing to the first character of the input string. The forward pointer moves ahead until a match or a pattern is found. So until a match is found, it will keep on moving ahead. Let us see how it works. So F pointer initially reads I, it will move ahead. It will read N. Since pattern is not found yet, or there is no matching pattern found, the F pointer will still move ahead. Now int is considered to be a pattern which is matched, but to confirm whether int will fall into the category of keyword or it will fall into the category of identifier, the F pointer will still move one more character ahead for its decision. Now it will observe that there is a space over here. Hence, it will say that a lexeme is discovered and the name of the lexeme that is discovered is int. Now, both these pointers will move at the first position of the next character. So, F pointer will move one position ahead and B pointer will be moving to the first position of the next character. So that is what is written. When a lexeme is discovered, lexeme begin is set to the character immediately after the newly discovered character. So wherever the newly discovered character was, immediately after that, the B pointer will be set and the F pointer is automatically forwarded to the next character. Okay, I'll just do it once again. So assume that this is my buffer. Okay, and as I said, my string will be F L O A T, float. I'll put one more space in my buffer. I'll add one more space and then there is this R. So this is float and result. Now if you observe, when the F pointer and B pointer are doing its work of identifying the lexeme, they will successfully identify this lexeme float. After float is done, F pointer will be pointing here and B pointer will also be pointing here. Now result is the next characters, or you can say result is the next lexeme that needs to be discovered. Now because R is only here and the remaining characters are not added to the buffer, when we add new characters to the buffer, all these characters will be overwritten. And what will be stored in buffer is E, S, U, L, T. The system, the lexical analyzer, has no way to remember the last character. It will never remember that it had read R before the buffer was refilled. I repeat, it will never remember that it had read R before the buffer was refilled. Hence, everything is overwritten. That means it won't be able to identify the correct lexeme, which was result. So this is the problem with one buffer scheme. Let us see what the slide says. So the slide says, if the lexeme is very long, it crosses the buffer boundary. So to scan the rest of the lexeme, the buffer has to be refilled. That makes overwriting of the first lexeme. So as I said, result ka R is overwritten and only ESULT will be saved in the buffer. So the identification of lexeme result is not going to happen correctly. Hence, we have another, that is two buffer scheme, that is introduced. In two buffer scheme, you have two buffers which are of the same size, that is n characters, and they are loaded alternately. Alternately means once the first buffer is full, then only the second buffer will be loaded. Also, these buffers are scanned alternately. That is, at a time only one buffer is scanned. As soon as we reach the end of the first buffer, then only the second buffer will be loaded and will be scanned. If the number of characters in the input file is less than the buffer size, then there is a special character like EOF which marks the end of the source file. Because we have two buffers used alternately, to make sure that we are not reading the empty spaces, or to make sure to identify whether the end of the source code is reached, there is a special character known as EOF which is added at the end of the file. This EOF is nothing but my sentinel. Thus, sentinel plays a very important role in managing buffer pair effectively. A sentinel is a special character which is often used at the end of the input buffer to mark its boundaries. In two buffer technique, there are two checks which we need to do. First, we always advance forward pointer and we check that we are not moving out of the buffer. If we have reached the end of the buffer, it is the duty of the lexical analyzer to reload the next buffer. Thus, for each character read, we make two tests. First, whether the buffer end is reached, and second, which character we have read. Based on whether the buffer end is reached or not, the decision to load the next buffer and to scan the next buffer is dependent. And based on which character is read, the lexeme will be identified. Thus, the sentinel is a special character which is not a part of the source program. It is just helping us to identify whether we have reached the end of the input buffer. So this is a small example which shows us that the end of the file has been reached. So EOF is a sentinel. EOF over here is also a sentinel. This was all about today's lecture. In my next lecture, I will throw more light on how do we make our lexical analyzer identify lexemes. So how lexemes are identified and recognized using regular expression is what I will be taking into the next lecture. Also, how a lexical analyzer is generated. How do we design a lexical analyzer? It is very interesting. I'll be taking it in the next lecture. Also, we start with syntax analysis and we will understand what are the various parsing techniques. Various parsing techniques means we will understand what are the various ways through which syntax analyzer is responsible for creating parse tree. Thank you for your patience listening.